Great. Thanks, Victor, for the introduction. I'm excited to be here. So I was talking to Payhan before, and so I was at Brown before. The first time I visited Brown was to give it was part of ballroom dance competition, right? So I was part of the Harvard ballroom dance team, and so we visited to compete here, and we did not win. But it was fun to be on campus, so excited to be here again. Okay, so yes, I'm at Illinois, and I'm going to be talking about this topic, error correcting codes, and how they imply privacy law bounds. And as I progress through the talk, please feel free to stop me. Let's make this interactive. All right, let's get started. Okay, so the privacy definition I'm going to focus on is going to be definition of privacy. I will introduce definition of privacy. Then I'll talk about a coding theoretic view of privacy. Then I'll talk about one specific lower bound for the definition of privacy via Packin. And this is the coding theoretic view. Then I'll talk about how we extend this to more general lower bounds. And then I'll discuss some new directions. Right? And again, as I proceed, please feel free to stop me, right? Or ask clarifying questions. Right? All right, so what is the privacy problem? So we have some data set with sensitive information, and it has, let's say, health records. And the health records could reveal which disease a patient has. Or let's say we have some census data, and it could reveal which household has certain attributes. Or it can also be social network activity, right? Suppose you lean maybe Republican or Democrat, and you don't want the pages you like to reveal your preferences for certain political parties, right? That could be social network activity. So this is all private data, and I want to be able to protect that, right? And so we want to be in this sweet spot right here. We want to achieve some utility out of our data, but get privacy, right? And so this is really going to be the core of what I'm going to talk about. There's some tension here between utility and privacy, right? And this is provable tension, right? And that's going to be the focus of today. Okay. All right, so why do we need privacy? We need privacy because of certain laws. So for example, the U.S. Census Bureau is bound by Title 13, and it restricts the employees of the U.S. Census Bureau so that they can't reveal your data to, let's say, marketers and to companies, right? And if they do, then they could literally go to jail, right? Or could be fined $250,000 or both, right? And so this is why we need privacy. Without such laws, I mean, people wouldn't enforce privacy, to be honest, right? And so the legal side is very important, and the legal side leads to the technical innovations we can discuss, right? And yeah, for my PhD dissertation, we worked a lot on producing methods for the US Census for 2020, right? Because it was built upon differential privacy, or they use differential privacy for most of the releases, right? And you might have heard in the news about that. There was some tension about that in different states, and some reforms about that. And so in 2030, they're likely going to use differential privacy again and want to be more ready, right? And we want to be able to talk about the tension between utility and privacy because that shows up all the time, right? If you want really good privacy, you can't get a perfect utility, right? And I'm going to talk about why that is. Okay, any questions so far? All right, so what's the problem? We want to allow the use of the data and protect the privacy of the data subjects, right? And ideally, we want to achieve both utility and privacy, right? But we can't always achieve utility and privacy, right, maximally. And that's going to be what I'll discuss via a technical lens of coding theory. Okay, so why differential privacy? We need differential privacy sometimes, right? And there's certain results in the literature. So for example, there is the Denonism paper in 2003. It's called the Fundamental Law of Information Recovery. It says that if you release too many statistics about data subjects, that could lead to a reconstruction of your entire data set, right? Blatant non-privacy, right? And this is the theoretical results, and you can also actually write code that would show the reconstruction of the entire data set just by getting aggregate sums, right? So that's the reconstruction attacks. And there's also membership inference attacks, right? Which is if you have some sensitive data set from some hospital, and the hospital is only treating people with, let's say, HIV positive status, right? Then the membership inference attack says you can infer if someone was used to train the data set or not. And that inherently reveals if the person had HIV or not, right? And that's a privacy violation. So we want to prevent reconstruction attacks. We want to prevent membership inference attacks, right? And we also know from previous literature that anonymization is insufficient, right? So if I have a data set, okay, what is anonymization? If I have a data set, and then let's say I have name, I have other sensitive attributes, and I have, let's say, HIV status. In the literature, it was known that one way to protect the privacy of individuals is just to strip the name, right, and call it private. That's anonymization, right? But it turns out that's insufficient, right, to protect the privacy of the people. And since the room's a little bit quiet, can someone tell me why that's insufficient? So you have a table, you have name, you have HIV status, and other attributes, and you only strip the name. And so the name doesn't link to the HIV status anymore, and you publish that. So why is that insufficient?
You just have tons of more attributes.
Yeah, essentially, yeah. So you can run. So Latina Sweeney in 1993, what she did was she bought voter rolls, right? And it had the names of people and had where they lived, right? And then she used anonymized data from a hospital, and she linked both data sets, and she was able to identify that the governor of Massachusetts at the time, William Weld, had a certain diagnosis, right? And she then mailed that diagnosis to the governor, and that resulted in changes in a lot of laws, right? And so the governor was saying, oh yeah, we need data for research. And so let's just strip the name and publish it. But that was insufficient because Lieutenant Sweeney was able to link the data sets to identify that he had a certain diagnosis, right? And so yeah, anonymization and aggregation is insufficient, right? But the French privacy provides a principal guarantee against these risks. All right. Any questions so far before I keep going? Yeah, please.
I have a question about the census law
Oh, yeah.
that you mentioned earlier.
Yeah.
I wonder, I suppose the law is not written in a technical way.
Oh, yeah.
So how did you interpret what's the privacy requirement?
Yeah, great. Yes. So the law, so it's a title, it's a U.S. code, right? Title 13, and it's up to lawyers to really interpret it, right? We can also interpret it too, but I don't have the legal expertise to do that. And so what happened is, there's a Title 13, and then the lawyers affiliated with Census Bureau interpreted it, and they talked to executives. And then after a lot of collaboration, they decided, okay, this is the amount of epsilon I want to set to actually protect U.S. individuals. Yeah, so it's really up to interpretation. You're correct, yes. And there's not one way to interpret it, and this is what lawyers do. Yeah, good. Any other questions, please? Okay. All right, so what do we want from a privacy definition? We want some utility. Right? We want to be able to do statistical analysis on data sets, right? Like, for example, if we have a data set containing HIV statuses of people, we might want to ask, what is the fraction of people in the data set who have positive HIV status, right? That would be like an average or a mean query, right? Or we can also train some machine learning models, right? And use that for future predictions, right? So that's the utility guarantee. And then we want some privacy guarantee. You want to be able to protect every individual in the data set against all possible attack strategies, right? Now and in the future. What does that mean? It means it should be immune to post-processing, right? If I get evaluate some function on the data set, no matter what I do on the function afterwards, it should not reveal anything about the individual in the data set, right? And actually, in the information theory literature, people just refer to that as the data processing inequality, right? It should be mean to post-processing. And then even if I have auxiliary information, if I get data sets from another place, right, I still can figure out if someone is in the data set, right? And so it should be immune to linkage attacks, right? And also, group privacy should be allowed. So usually, the privacy definition allows you to protect the privacy of a single individual. But what if I want to protect the privacy of me and Victor, for example, in the data set? It should allow for that, right? And that's group privacy, right? OK. So today, I'm just going to talk about the basic definition, the pure definition. But there's a variety of definitions in the literature right now, right? There's the pure definition, there's the approximate definition, there's the Rainey definition, FDP, and others, right? I'm just going to focus on one. OK. So the definition was introduced in 2006 by Dwork and others. And it's motivated by work by Dina and Nassim. I really like this paper. So again, people refer to this as the fundamental law of information recovery, right? Releasing too much aggregates about the data set can lead to reconstruction of your entire data set, right? And to me, this paper introduced the first coding theoretic view of differential privacy, right? And there's also other works by Dwork, Nassim, and Blum, and others, right? OK, so what is the definition? The intuition is you have a statistic, like a mean, for example, or sum. And the effect of any individual, right, in the data set should be close to nothing. So that's the intuition we're trying to go for. Right? And this should be a worst-case notion. We want to protect against all possible adversaries and any kind of individual. Right? So I put a star here. Right? Because, I mean, there's one thing to have a definition that's information theoretic, and there's another side to it. You need to actually implement it on a computer, right? In which case, you definitely need like cryptographic primitives to actually implement it in a way that's correct, right? And I'm going to discuss just a few primitives. So usually, with differential privacy, you're computing some statistic, and then you're going to compute some noise to add to it. How you actually compute the noise could actually, if you do that in an insecure way, everything falls apart. Right? So it's a worst-case notion. It's an information theoretic definition. But again, you need to implement it correctly. This is why there's a star here. OK. All right. So again, now let's go through slowly the math. So we have an algorithm A, and we say it satisfies epsilon differential privacy if, for all neighboring data sets, x and x prime. And the neighboring data sets notion here says that this data set's x and x prime should differ in exactly one row. So if the distribution on the first data set is epsilon away from the distribution on the second data set, right, we'll call it epsilon dp. Right? So this is the intuition. Yes, please.
Why is the query producing a distribution rather than just an answer?
Good. Yes, good question. So why is it a distribution rather than an answer, right? So it has to be randomized because if not, there's no finite amount of epsilon that would ensure the definition.
I see. So this is saying post-differential privacy processing.
Yeah, exactly. Yeah, this is saying for it to satisfy differential privacy, like, yeah, this needs to be randomized. Yes, yes. And yeah, again, you can show. I mean, once I put the definition in the subsequent slides, you see that you can actually show that there exists no finite epsilon for certain queries that would get you to satisfy the differential privacy definition. Yeah, but great question. And yeah, the smaller epsilon is, the more privacy is ensured. And that's the intuition. Any other questions? OK, so here's the definition. So for all sets, all measurable sets, we want the probability that the algorithm evaluated on this dataset X, right? The probability that the algorithm evaluated on dataset X and outputting a specific thing, we want the ratio of this probability when the data set is x versus when the data set is x prime, we want this to be bounded by 1 plus epsilon. Right? And this, again, is the closeness definition. Right? And so you can see here, if epsilon is 0, it's saying if I'm in the data set versus if I'm not in the data set, this probability of outputting any specific thing should be the same. Right? And so if I increase epsilon a little bit, then it's saying, OK, I want it to be almost the same. And so the larger epsilon is, the less stringent my privacy would be. And the smaller epsilon is, the more stringent my privacy would be. Right? Yeah. Yes, please.
Is there a reason why we use this notion of like distribution distance versus like other kinds of distribution distance?
Good. So why even use this ratio? So this is multiplicative. Right? It could be additive instead. Right? Is that what you're getting at?
Yeah, or like something like TV distance.
Exactly, yeah. So the TV would be additive. So with the TV, for example, it would be this minus this, right? And then you could say it's less than or equal to epsilon, right? So you could do that, but it wouldn't enforce like a worst case notion, right? It would be like an average notion. Because the TV, right, remember, is like the sum over all possible outputs, right? So it's like an average notion. But this is the worst case overall sets T. Yes, that's why. Yeah. But it turns out this definition, so there's an approximate version where you add like a delta here. So it turns out that if epsilon is 0 here, and if epsilon is 0, then this actually would imply the TV definition. Yes, but it's not the other way around. If you have like a TV enforcement, it would not imply this definition. Yeah. So this is more like a point-wise privacy guarantee. Again, the worst case overall sets, and TV is like an average type guarantee. Yeah, great question. But people have definitely tried to use the TV distance, right? And there's been works that show that that's insufficient. Yes. But TV would be sufficient, in my opinion, if, for example, you enforce that the TV parameter has to be, let's say, cryptographically negligible. Then I think it's fine. But if you're saying it has to be constant, then it would not be sufficient. Yeah. Good. Any other questions? Yes, please.
What's a query?
Oh, yes. Good. What is a query? So a query could be a mean. So I have a data set, X. The data set contains the ages of people in this room. The query could be, get me the average age. Right? Or it could be, get me the minimum age. Who's the youngest person in this room? So the query is a function on the data set X.
Isn't that kind of like rolled into all algorithms where like, there's an algorithm that runs that query on the data set, right?
Yeah.
Okay.
Yeah, I mean, yeah, you could roll it into the algorithm.
Okay.
Right? But I just wanted to be explicit and put the query here, because the query actually does matter.
Right.
So there's some queries that have infinite sensitivity, meaning they're really, really sensitive. Right? Like, for example, the inverse query has infinite sensitivity. But the queries I'm going to talk about are not as sensitive, meaning it's easier to hide the effect of a single individual in the data set. So this is why the query, being explicit with the query actually does matter. Yeah. So differential privacy just can't hold for all queries, for sure. Like, it's literally impossible to hold for all queries, yeah.
Doesn't the definition say for all queries, though?
I mean, for all queries in some set.
Oh, okay.
Yeah, so, I mean, what I mean is for all queries in the set. Not all possible queries ever.
Okay.
Yeah, that's not possible.
That seems very
Yeah. But good clarification, because, yeah, it does matter what the query is, and it does matter if it's baked into the algorithm also. Yeah. Any other questions? Oh, okay, good. All right, so the actual definition isn't to use 1 plus epsilon, but it's to use e to the epsilon, actually. And assuming epsilon is set to be small enough, this would be about 1 plus epsilon, right? But usually, it's not set to be small, right? But yeah, it's set to e to the epsilon, actually, in the definition. Okay. So the probability is over the randomness of the algorithm. and not over the query and not over the data set, and that's important. Right. Okay, so this talk is not about the mechanisms for ensuring differential privacy. There's a lot of them, like Laplace mechanism, Gaussian, exponential, geometric, and others. And the goal here is you have some query, like a mean, right, a median, or something else, a machine learning query, and you want to add noise of some sort to hide the effect of a single individual. That's the high level. And here's the visualization I did in 2019. So you can visualize the epsilon parameter, the privacy parameter, and the error for simple queries like sums and averages, right? So the smaller epsilon is, the more your error is, right? And this visualizes the trade-off between utility. So this is more useful, utility and privacy, and this is more private. Right? And now the question is this inherent, right? And we can show this precisely. Okay, so we can show this via a coding theoretic view. So in coding theory and in information theory in general, there's this notion of a channel. You have a message, and you encode the message somehow, and then the message goes through a channel, and the channel could disrupt the message, and you decode the message, and you get M hat. And ideally, you want to recover the message M hat, M from M hat, right? And so you can think of this channel as the differentially private mechanism, and you can think of this message as hidden if I'm in the data set versus if I'm not in the data set, right? So the intuition is the privacy of the message is ensured if I can't reconstruct M from M hat, right? And M indicates if I'm in the data set, right? So here's the 2D visualization, right? So here's so you have a query A, for example, and you have a data set. These are different data sets, right? And you evaluate the query on the entire data set, and you need to add some noise to kind of hide the effect of a single individual. You add some noise here, you add noise, and this is the decoding radius, right? So here, so AX, so this is the query, and this is the data set, and you need to add some noise to ensure differential privacy, right? And these are the code words of an error correcting code. Right? So this is a code word, code word, code word, right? And if you add so much noise that it's outside of the code and radius, right, that could be good for DP, but bad for utility, right? And so this really sums up, I would say, in 2D, the coding theoretic interpretation, right? That code words that correspond to the queries, right, that are being evaluated on the data set. Yeah. Okay. So I talked about reconstruction attacks, determinism reconstruction attacks, just briefly. And early results, especially this result, shows that if you answer too many queries too accurately, that could lead to a reconstruction of the entire data set. And again, this is called the fundamental law of information recovery. And that's what Cynthia DeWart told me it's called. And yeah, I think it's a really nice result, right? Yeah. Okay, so now let's get into some details, right? Any questions about what I just talked about? Yes, please.
Yeah, sorry, I don't understand the coding theory perspective because it meant a data itself will not be a code word, right?
Yeah.
It's just a unencoded thing.
Exactly.
Yeah? So,
yes.
So there is no inherent distance or anything in
Exactly.
the data set itself. So
Exactly.
How is this?
Good.
Mm-hmm.
All right. So why does this? Again, this is a projection to 2 dimensions, right? But this really is a data set, right? And this could be anything, right? And this, you can think of this as the code word, right? So this is the data set, could be anything. And then, just like, with normal error correcting codes, right? You have some message. The message could be anything. And you encode the message, right? And you get these things, right? So this is the queries that are being applied to the data set. And again, this could be any data set. And then you map it into some space, right? It's into some code book.
Yes.
You
So the
see?
query and the onset map them
Into code words, exactly. So the data set is not the code word. You map the data set to code words. And these are the code words.
And we want these code words to not be close enough.
Exactly, yeah. We want them to have a minimum distance. Yes, yes. Because for it to be recoverable, you need some minimum distance, a notion of minimum distance. Yes, yes. Good. Any other questions? Again, this is a 2D visualization. It's not as accurate. Okay. All right. Okay, so now let's talk about queries. Let's talk about a simple query, the counting query, right? So queries do matter, right? And we're going to talk about a simple one because if you have a more complicated one, the math just isn't going to work. Okay, so a counting query is specified by a predicate, right? It takes in a datum or a record, and it could output 0, 1. So you can think of this as being, for my record, do I have a sensitive attribute or not? Do I have a sensitive disease or not, right? And then you can get a fraction of how many people have like a positive predicate on the data set. And so we're going to prove lower bounds for this counting query type, for this counting query. And it turns out the counting query, a lot of people study it because you can reduce getting histograms into counting queries. You can reduce getting CDFs into counting queries. There's a lot of functions that can be reduced to counting queries, right? And so this is one reason I want to focus on studying it. So you can have a data set. This is the data set. And then this is your mechanism. And the adversary would ask for the answer. And you want to make sure to go through the channel to add enough noise, right? And the analyst asks certain queries and gets results back. So this is what we want. And we want Q here to just be a counting query. Okay. All right, so here's what we're going to show. And this is shown by Hart-Talwal, Moritz and Canal-Talwal. So if you have an algorithm, and the algorithm answers all the queries in some set Q, and the algorithm satisfies epsilon delta dp, then if the algorithm answers every query in Q, so within alpha, then we can get this lower bound, right? Okay, let's interpret the lower bound. So this is saying that the error, so the error is essentially alpha, right? If we have a large data set, the error wouldn't be as much, right? If our privacy parameter is large enough, meaning we're not ensuring as much privacy, the error wouldn't be as much, right? And then again, also, the privacy parameter is not too small, the error wouldn't be as much, right? And so there are certain parameters that determine how much error you're going to have to satisfy differential privacy, right? And this is quantified by such theorems.
What's the delta?
Delta, I didn't talk about delta, but delta is another, yeah, I should have put the definition, epsilon delta dp. So what I put there is epsilon 0 dp, right? But delta is saying that the epsilon 0 dp definition holds a probability 1 minus delta. Yes. So it's like a high probability bound on the pure definition. Yes. Good. Yes.
The epsilon 0 definition was the probability over the randomness of the algorithm.
Mm-hmm.
So you're saying there's like you wrap that in a probability, and then what is the randomness over?
So the randomness is over the algorithm. So
The probability over the randomness of the algorithm twice.
over the algorithm, yeah. It's still over the same algorithm, A.
But like, because wasn't the original definition like the probability is within epsilon of something, of some other probability?
Mm-hmm.
So I guess I don't exactly know what it would mean to say like the probability that that thing holds is bounded, because it seems like we're already using the expectation over the randomness.
Good. So this is about the approximate definition, right? So why is that true? Yeah, okay. So you can actually think of the pure definition as a privacy loss random variable itself. Right? So what is the random variable going to be? Again, A is a randomized algorithm, right? So you can think of it as a random variable. Now you can quantify the probability when I'm in the data set versus not in the data set, right? That's its own random variable. And so if you take the log of that ratio of the probability, that would give me, or that should give me at most epsilon. Right? So it's a random variable. Now I'm saying I want the random variable, I want the probability that the random variable is greater than epsilon to be at least 1 minus delta. That's the epsilon delta dp definition. Does that make sense? Yeah, so, I mean, yeah, it's just like a random, the ratio of the probabilities, the log of the ratio of the probabilities is a random variable. And now we just want,
I guess why is the log of the ratio of probabilities a random variable? It seems like it's fixed.
oh, but then A is randomized.
Oh wait, because it's for.
So A is going to toss some coins, right, to give me some
Is it
alpha.
like the randomness over, because we do look at like, you said like it's the worst case over all the, it's kind of like a point-wise,
Yeah.
the pure definition. Is it like the randomness over different points?
So it's the randomness over the algorithm. So the algorithm, how's the algorithm going to work? It's going to evaluate the data set, right? Let's say get a mean. There's no randomness. And it's going to add some noise.
Yeah.
So the addition of the noise makes the whole thing random.
Right.
And so that's where the randomness is coming from. That's why the algorithm itself is going to be random. And now you can then quantify, okay, what's the probability that the algorithm, after adding noise, is going to output a certain thing, right? And so you take the ratio of the probabilities, right, and you take the log. I'm taking the log because, remember, the ratio of probability should be e to the epsilon. And so I want the log to give me epsilon itself. So sometimes it might give me epsilon, sometimes it might not give me epsilon, because it's a random variable. The randomness is coming from the algorithm A.
Okay.
Yeah. And then we could say, okay, we want to enforce that constraint with probability 1 minus delta. So we can enforce the constraint all the time. That's the pure definition. But we can relax it a little bit just to get a little bit more gains, and that's the approximate definition. Yeah. Does that make sense? Okay. All right. Okay. So here's the lower bound, and we're going to prove it by two things: group privacy and packing. So okay, we have an algorithm. It satisfies epsilon delta dp. Okay, here's the definition I talked about without the m, and so we're going to prove this bound, right? So we've been talking about data sets that differ in exactly one row, but what if the data set differ in m entries? What happens? This is what happens, right? We can use the hybrid argument. I mean, okay, so we have a data set, x, and we want to go to x prime, and they differ in m rows, right? So we're going to just change one row, right? So z0 and z1 differ in exactly one row, and they keep differing in exactly one row until they get to x prime, right? And so we start here. Right? And we know this definition is going to hold by the French privacy. So essentially we're asking, how does our epsilon delta dp definition, which holds on neighboring data sets, how does that imply a definition that holds on data sets that differ in, let's say, m rows? Okay. So we know this holds by the definition on neighboring data sets because z0 and z1 are neighboring. And so we just keep applying the definition until we get to x prime, right? And so we're going to change m rows. Right? And so we get here. All right, any questions about this? Okay.
Sorry,
Yes, please.
What should I infer from this last bound? Does that mean it's probably will just be dominated by 1 minus e to the epsilon?
Good. Okay. How do we interpret this?
Okay.
So with the normal definition, when they differ in exactly one row, we have an epsilon parameter for privacy, and we have delta parameter for privacy. Now, when they differ in m rows, where m could be large or small, then epsilon becomes epsilon m. So if I'm trying to protect m individuals, then my privacy parameter would weaken to epsilon times the number of individuals I'm trying to protect. Right? This is it. And then now what happens at the delta? Something similar happens, right? But it's a little bit more conservative in the transformation, right? And this becomes m times e to the epsilon m. So the deltas and epsilon parameters add up for privacy. Yeah, that's how to interpret it. To answer your question?
Yes,
Okay.
thank you.
All right, so, yeah. So we just, yes?
Yeah, oh, yeah,
Oh,
this,
okay.
this is the interpretation.
Exactly, yeah. So this is what we just proved.
Yeah.
We proved this holds by the hybrid argument, and if you divide both sides by e to the epsilon m, you also get this, right? And now we're going to use this to prove a lower bounding utility. Okay. So first of all, let us now go back to the coding theoretic interpretation. Right? We have a data set diffused in m rows, right? And let's consider disjoint subsets of some output space y, right? And now we have an algorithm that is supposed to be epsilon delta dp. That's a guarantee. And suppose the algorithm is accurate, meaning that for every data set x, right, you should output something in the output space with a constant probability. This is the accuracy guarantee. Without this, there's like trivial ways to make it satisfy dp. Right? Okay, so if we have this accuracy guarantee, meaning we output something correct with a constant probability, then this is the packing bound, meaning we can't have too many such data sets, right? And this is what we're gonna show. Okay, so here's the proof. This is essentially our assumption, and this is the data set, right? And this is the output space of the data set, the output space of the algorithm on the data set, right? So we assume this is disjoint, and every probability is upper bounded by 1, so we have this inequality, right? And because this is disjoint, we get this summation over the data sets, right? And now we use the bound we just proved, right? Because we know x0 would differ from x by at most m, so we use the bound we just proved to get this right here, right? And then because we're summing over this data set C, we can bound it by the collection C, right? And that's the proof for packing. Okay, so what is the implication of packing? Right? We proved packing and we proved group privacy, and then we can use that to actually show this bound, right? And to me, it's more important to actually interpret this bound. There's additional steps to actually proving this that I'm not going to go over here. But essentially, the packing lower bound technique is really what's used for proving most lower bounds for pure differential privacy. And that's also the technique we use for our paper too. Okay, so let's interpret this. First of all, there's a half here. Can someone tell me why there's a half here?
Because it's from there, there.
Oh, actually, yeah. That's not quite it, but yeah. Yeah, but yeah, okay. So the reason why, I guess, yeah, okay. The reason why this query should give me something, should give me 0, 1. There's like a trivial mechanism that could just give me always a half for every data set, right? And so that's not accurate at all, but that's going to achieve this bound, this accuracy bound. This is why the half is there. Yeah. Yeah. Okay, and so what's happening here? This is saying that if my privacy parameter is very small, meaning I want to ensure privacy very stringently, then my accuracy loss might be large. If my data set is large enough, I might not have to pay that much in accuracy loss, right? And then if my domain size is large, I might also I might have to pay a lot in privacy. Right? And so this gives an operational interpretation of differential privacy. Right? The use of stringent privacy parameters in terms of epsilon and delta might lead to loss in utility. And that goes back to my first slide. And we proved this via like a coding theoretic view. Right? And that's just the whole, this is the main point. Yeah.
So I just have a quick question. So is this bound for only some query, or is this like a family of queries that this bound will hold?
Good. This is for a family of queries. It's for the counting queries. Yes.
Yeah.
It's not for all queries. Good.
Do you think we'll have like a characterization? Which query will lead to which code that will have the back bound?
Yeah, that's an open problem. Yeah. So we know for counting queries we can characterize it. This is bound. This is tight. The Laplace mechanism achieves this bound. Right? The Gaussian mechanism achieves this place. Right? And so we know this is tight for counting queries. For certain queries, like let's say the inverse query, this is absolutely tight. That's like the worst query you can think of. Right? And yeah, a good question is, can you characterize like lower bounds for all queries? Yeah, that's an open problem. We don't really know how to do that. Yes.
Is the inverse query the sum of the inverses? Or what?
The inverse query, in one dimension, the inverse query could just be 1 over x. So let's say I give you x, and, I ask for, okay, your query is give me the inverse of my data set, and I always give you 1 over x. That's the inverse query in one dimension. It would be the inverse of the entire matrix.
Oh, okay.
Yeah, so instead of just 1 over x would be x inverse, or x to the inverse if it's not invertible. And that query has sensitivity infinite, meaning if I change one data set, if I change one row in the data set, then the maximal change might approach infinity. And you can see why that is. Right? So that query is just really bad for the differential privacy. So we try to handle simple queries like means and averages and things like that. Yeah. Yes?
Is there practical ways to go around it?
For the inverse query?
Yeah.
Yes. Yes. So, for example, one way to go about it is to make sure your input is not unbounded. So if, let's say, you guaranteed, so if I have a data set, then I could try to enforce that the data set can have any data values that approach 0, for example. Right? So that would ensure that even for the inverse sensitivity query, my sensitivity would not be infinite. Yeah, so that's one practical way to go about it. But the problem with that is that leads to like biases in the query. Yeah, the query answers at least. Yeah, but good point. And there's practical ways. Like for example, my thesis, I was doing linear regression, right? And linear regression, I mean, it's also a very sensitive query, has infinite sensitivity. But the practical ways we went about it is just to clip to make sure that we never get infinite sensitivities. Yeah, and that made sure I could write a thesis. Yeah. So, good. Any other questions? Okay, so now we're able to extend this to actually more complicated lower bounds. Like for example, for lower bounding data from a Gaussian, for example. So what I mostly talked about has been simple queries and simple data sets, like one-dimensional, for example. But you can have data from, let's say, genomic data sets, right? Multi-dimensional. Right? High-dimensional distributions are just very hard to handle sometimes because of the curse of dimensionality. Usually, utility bounds would have dependence on the dimension. And if the dimension is like much higher than your data set, for example, it's pretty bad. Right? So one way to go about it is just to make certain assumptions. That, for example, your data set is from a normal distribution, in which case, instead of needing an exponential number of points to really accurately estimate your function or query, you can just get a polynomial number of points instead. Right? And that's how we handle high-dimensional distributions from nice families like sub-Gaussian distributions. Right? Okay, so for a recent paper, we asked the following question: if we have a data set that's drawn from a normal distribution that's high-dimensional, right? So it leaves the mean and the covariance live in d dimensions. Then can we accurately estimate the Gaussian? Meaning, can we learn the Gaussian to within alpha TV distance, right? Which is this. And so it turns out you can if you learn the means in Mahalanobis distance to within alpha, and if you learn the covariance to within alpha, right? And that's what the algorithm does. And so here's the lower bound we have in the paper. And this says that every epsilon 0 dp algorithm, given n samples from a Gaussian, is going to need this amount of data. Right? If you want to estimate the Gaussian to within alpha TV. Right? And I'm not going to prove this statement, but essentially it follows from what I talked about with packing lower bounds. So we use the same proof techniques and extend it to the Gaussians in d dimensions. Right? And this is why I went through the simple proof for the packing lower bound. So we just extend the same technique to show a lower bound on the sample complexity. Okay, let's interpret this. This again has the same parameters, the inverse polynomial dependence and the privacy parameter. And then it has other things like now a dependence on the dimension, right? And then it has a dependence on the condition number, or let's say the largest eigenvalue in a data set. And so we prove that, again, the privacy utility trade-off is inherent. Right? If you're trying to get high utility via alpha, for example, you're going to need a lot of data potentially. That depends on how accurate you want to be. Right? And this does not show up in other privacy, I think, definitions. Right? But for differential privacy, it's like inherent. You need big enough data if you want to accurately estimate. Yeah. Okay. All right, so that's the gist. And the proof sketch, so we have condition number lower bound via carvings of packings. Today I talked about packings. And then we have other things in the paper to actually prove this lower bound. Right. Yeah. Okay, so I just wanted to give you a sketch of the proof of the lower bound for covariance estimation. And I just want to be cognizant of time, and I would prefer to have questions. Right. Okay, so to summarize, I mean, you can prove privacy lower bounds via coding theoretical lengths. Today I showed you proven lower bounds via the use of packing. Right. How many balls can you pack in some space? Right. How many code words can you pack, even within some decoding radius, how many code words can you pack in some space? Right? And a lower bound of how many packings you can have can imply a lower bound for differential privacy. That's the main technique we talked about today. But it's other lower bound techniques in the literature that I didn't discuss, like fingerprinting codes, right? Which was initially used actually for traitor tracing in the cryptography literature by Bonnet and Shaw. And that also leads to lower bounds. I didn't talk about that at all. But that's another lower bound in the technique, right? And for our paper, we show that if you're trying to estimate a d-dimensional Gaussian to within like a very small TV distance, you're going to need samples that depend on the dimension, right? So if you have 1,000-dimensional Gaussian, you're going to need 1,000 squared, for example. And we show this is inherent and prove the lower bound, right? And no one proved the lower bound until we did. Anyway, so the summary is, yeah, I mean, lower bounds, in my opinion, are very important for differential privacy to understand how many data samples do you need to accurately estimate, right? And the upper bounds you can achieve by certain mechanisms, just by adding enough noise. The Gaussian mechanism is there. The Laplace mechanism is there. You have a function. You evaluate the function in a data set. You add noise, you achieve the upper bound. But to me, the lower bound is more interesting. Yeah. Okay, so what I showed you was for the central model, meaning there's some trust. Right? Let's say I'm the US Census Bureau. I get everyone's data set, for example, and then I have to add enough noise to ensure differential privacy. That's a central model. But it's other models, for example, like the local model, where if I'm Google and you don't trust me, then you can perturb your own data before you send it to me. Right? That's the local model. And there's lower bound techniques that apply in that setting too. I didn't talk about that today. Right? And for future work, we need to understand the precise trade-offs between like the code and theoretic lengths by the code rate and the required noise for differential privacy. Right? That's an open problem. Right? But the gist of today was just to show you that, I mean, usually for proven lower bounds, you need a code and theoretic lengths. Right? Yeah, so I'm going to end here. And if you have any questions about any part, please let me know.
Any questions?
Yeah, please.
How close are these lower and upper bounds?
Yes, good. So it depends on the model. For counting queries, they're tight. I mean, they tight up the constants, big O. For counting queries, they're exactly tight. For the d-dimensional Gaussian estimation, they're also tight. In our paper, we have upper bounds based on sum of squares hierarchy and lower bounds based on pack-in, also tight. For certain queries, like linear regression, it's not quite tight. Right? If you also queries like min and max that are more sensitive, also not tight. For for general quantiles, also not tight. So yeah, it depends on the family of queries you're considering. Yeah.
Do the constants matter?
Yes, the constants matter a lot. But for this papers, I mean, we just kind of hid the constants. But so usually people treat epsilon not in terms of like O of epsilon, but unfortunately, when they're talking about the sample complexity, they just like put big O, right? But the constants could matter a lot. Like, I mean, even if you have like 1,000 times the expression 1,000 times d squared, it could really matter, right? Versus just d squared. But just for the simplicity of our results, we just did everything in terms of big O and big omega. Yeah. But yeah, the constants absolutely matter. Yeah. Yeah.
For the covariance estimation order bound,
Mm-hmm.
does it not generalize or not zero delta?
It does, yes. So for this one I just presented, the mean is 0. Yes, but in the previous slide I showed that if you estimate the mean to within Mahalanobis distance of alpha, and you estimate the covariance to within Mahalanobis distance of alpha, then that would imply a TV distance on any mu and any sigma. Yeah, but for this I just showed, yeah, good for noticing. Yeah.
And then for your previous lower bound,
Yeah.
I guess like it was like in terms of log of the size of the
Yeah, good.
log delta.
Yeah, so
These aren't exactly related, so I was wondering, would you just want to set delta based on like the size of x?
For alpha to be lower. Well, you're saying how do you set the parameters? Like,
yeah, like I guess like x is like something you're given, like that's something, but you can choose delta.
yes.
Would you, is there like some optimal where it's some trade-off? I guess?
Yeah, you can probably numerically try to understand how to set delta to achieve that. Yeah, but I didn't explore that, honestly. Yeah. And I think related to your question, so in the previous lower bound, there was like a dependence on the size of the universe. I think it was x chi. But here, there's a dependence on the condition number, right? The size of the universe here is infinite because the Gaussian distribution is infinite, right? But for the Gaussian distribution, you can upper bound like a VC dimension in terms of this, right? So I thought that's actually what you were referring to initially about the size of the universe chi, because that doesn't apply to this setting. Because for the Gaussian distribution, again, the size of the universe is infinite.